Hello, my name is Christopher Robert Stum, and this is the first of a sequence of 3 videos dedicated to explaining a process known as completing the square. In this first video, I'll explore the definition of a perfect square, and in the second video, I'll use that definition to explore the process of completing the square, and in the third, I'll be exploring various applications of the process of completing the square. So I want to provide a geometric interpretation of the definition of a perfect square. Suppose we want to find the area of a square, such as the one shown here. We know that the area, because the length of one side is equal to another, the area is given by the formula of multiplying that length by the other length, so the area being equal to the square of the lengths, that is, the length squared. By the property of equality and substitution, because L times L is equal to A, and in turn A is equal to L squared, we can set L squared equal to L times L by simply substituting L squared in place of A, such that we have L squared equal to L times L. Observing that this statement says that the area of the square is synonymous, that is, it is equal to the length of each respective side multiplied together. If we wanted to plot a graph with coordinates x, y, such as the one given here, this is our y and this is our x-axis, that would illustrate the various solutions for any side length of x that we would have for its area. That graph would look something like this, where this is the graph of y equal to x squared. This graph would usually take the shape of a parabola, that is, a shape symmetrical about some axis, in this case the y-axis. Here we observe that parabola have an axis of symmetry, that is, in this particular instance, the axis of symmetry is the axis over which one side is reflected, so that's the y-axis, and that would be x equal to some value h, where h in this case is 0, so x equal to 0 is the y-axis, and so this is the axis of symmetry. If we wanted to pick a point x and denote that as our input, that is, if I pick x, the output we would observe is again synonymous to the area of that square, and so the input x would correspond to the length of one of those sides of the square. Because this is the point x equal to h, which may or may not be 0, in this case it is, but if it weren't, then this would be shifted over, or over this way. But we would observe that that distance we picked would actually, that is the length of the side, would be equal to x minus h, and that's equal to the length of that side. That is, the length of the side of the square is given by x minus h, because here we have x equal to h. And so, bearing that in mind, we observe that the length of the square in this particular instant could be synonymous to x minus some constant h, where the constant in question is within the set of real numbers. And so this is x minus h. Bearing this in mind, let's write this expression up here so we have a little more room to work with. L squared equal to L times L. If we substitute the definition of L, which is said to be equal to x minus some constant h, we would observe that now this is of the form x minus h squared equal to x minus h times x minus h. Suppose that h is equal to the opposite of 1/2 times the quotient of b over a, where b and a are constants, and they're real constants, that is, they're values within the set of real numbers. We could simplify this to h being equal to the opposite of b over 2a. Now you're probably wondering where this came from. In fact, to actually see that h is indeed equal to the opposite of b over 2a, we would have to apply the process known as completing the square. So hold on to that question, that will be answered, but in the second video. For now, assume this to be true, because as we'll soon see, it is true, that h can analogously be defined as the opposite of two constants multiplied by 1/2. That is the quotient of two constants, b and a. Substituting this value in place of this equation, we observe that because we have x minus the opposite of b divided by 2a squared. This in here becomes x, a negative and negative, that is the opposite of the opposite becomes positive, and as such, this becomes x plus b divided by 2a. In turn, what this means about our square is that now we're claiming it to have dimensions x plus b over 2a, which, again, it's the same thing. It still has length L, length L. We're just saying this is the value of L. It's the result of summing some variable x with the quotient of a constant b and a multiplied by 1/2. So x plus b over 2a. And those are the dimensions defined thus far. And substituting it in this half of the equation, we have x plus b divided by 2a. Again, now this is saying the exact same thing that it has for the entirety of this video, which is that the area is synonymous to the product of two lengths of a square. And so here we have the definition of those lengths. Suppose that we were to multiply, that is, expand this side of the equation. So we would have x plus b divided by 2a squared equal to, by the property of distribution, we have x squared plus b over 2a, x plus b over 2a, x plus b over 2a squared. Now this is very interesting, because on this side what we see is that we're saying the area of the square is analogous to the product, that is the result of multiplying both of these sides. So here we can geometrically interpret a square with side lengths equal to x plus b over 2a and x plus b over 2a. Basically, this is here. On this side, however, we're saying that we can get the exact same area, but rather than having a product of two sides, that is, by just taking the area of the shape, we would instead sum the areas of four separate shapes. In other words, here we have an x squared, which is really x times x. So in that way, this is analogous to a square with dimensions x and x, such that when we multiply them, we get the area for that square. Correspondingly, that would mean that here we have some shape with a width of b over 2a, where we could choose either way, but I'm just, for the sake of simplicity, going to assume the height to be x, such that these are the same height. So b over 2a need not necessarily be greater or less than x, but as we'll soon see, that won't matter. It will still fit together all the same. But bearing this in mind, this would imply that this area is analogous to the multiplication of this times this, and we have two of these, so that would be plus another shape, same height, x, and the width of b divided by 2a. And lastly, if we have this width, then the height, since this is plus b over 2a squared right here, we would have b over 2a, b over 2a, and so we would have something of the form b over 2a, b over 2a. Note that we have two squares and then two rectangular figures. Interestingly enough, we're claiming again that this area is the same as this. How might we actually show this to be true? This is where the definition of a perfect square actually comes into play, is that geometrically we might interpret this as follows. We would say that how could we fit these pieces together in such a way that they would form this shape, a perfect square? Well, observe that if we took this square, x by x, so I'm going to use different colors so as to distinguish one shape from another. This will be our x by x. Because we have the similar height of this shape equal to x as well, we could align it along this side such that this distance would be analogous to b over 2a. And since there are two of these, we could in turn do the same thing with this one by placing it here. Observe that since this is a distance b over 2a, And this also is a distance b divided by 2a, that this is b over 2a, and this is b over 2a, which is given by the last piece. And so we put these together, and indeed we see that collectively they form a perfect square. That is, as we can see, this is equal to a length x, and so on this side, since this is x, together we see that the entirety of this side is x plus b over 2a, and so they are indeed the same figure, and thus the same area. So this is the definition of a perfect square. That is the geometric representation of what that would entail. We can simplify this side algebraically, but it will imply the same meaning again, the same geometric model that I've shown here. That we've put four different components together in such a way such that they're not synonymous to a perfect square. Observe here that we have like terms. We can thus combine them such that x plus b over 2a squared is equal to x squared plus, combining these produces a 2b divided by 2a x. We have a cancellation of coefficients here such that the result is b over ax. So this simplifies to b over ax. But again, note that that doesn't change what we've got here. We still have, if we break this back apart, two rectangles with dimensions b over 2a and x. This is just a variant of algebraic simplification. And so now it's plus b divided by 2a squared. So the first thing and most important thing to take from this entire video is that a perfect square is defined by the equation x plus b divided by 2a squared equal to x squared plus b over a x plus b over 2a squared. This is the algebraic definition that we're going to use for a perfect square, and thus the geometric model to interpret that is where we have some perfect square, two rectangular values, and then a smaller square. This is what we will use to explore the process by which we complete the square in the next video.